Hello, my wonderful students. Welcome back. We are going to be starting Unit 8, which is all about sequences and series. And we're going to kind of jump around a little bit. We'll see. But today we're starting with 8.1, which is just an overview, like a nice little review of what are sequences. And then we kind of look into kind of what is a series, okay? So we have 5 objectives. It's going to be a little bit longer of a lesson, so take breaks as you need. So our first objective is we're going to use sequence notation to write the terms of a sequence. Okay. And then this should be review from hopefully Algebra 1, Algebra 2, so on. Second objective is that we're going to look into factorial notation. So what does that mean? What is a factorial? That will be new. Then we're going to use summation notation to write sums. So sums is just there's no S on that, sorry. Sums are just what if you just add up a sequence, okay? Then we're going to find the sum of an infinite series. So if something goes on forever, how do you add it all up, right? Because you can't add numbers to infinity. And then we're going to use sequences and series to model and solve real life problems. So we're just going to start with some basic, see if you can identify the pattern type thing. So I want you guys to try these on your own. It says identify the pattern to find the next 3 numbers, assuming that the pattern continues. So we go ahead and assume that the pattern is continuing. I want you to pause the video and see if you can come up with the next 3 numbers for all 4 of these patterns. Okay, so let's look. Hopefully you've given it a shot. For number 1, right, 1, 4, 9, 16, 25, these are all perfect squares, right? This is a perfect square of 1, perfect square of 2, and so on and so forth. So this is 5 squared, so the next number would be 6 squared, which is 36. And then the next number would be 7 squared, which is 49, and then 8 squared, which is 64. And then the dot, dot, dot just means it continues on forever. Okay, for number 2, let's look here. And sometimes if you don't realize what's happening, you can just start writing things down. So here, I subtract 6, right? To go from 60 to 54, I subtract 6. And then to go from 54 to 66, right? 54 to 66 is I add 12. And then I subtract 6. And then 60 to 72, I add 12. So then the next number would be I subtract 6. So 72 minus 6. Sorry, my dog is pushing my computer around. 72 minus 6 is 66. And then I add 12, which is 78. And then subtract 6, and I get 72. Okay, so sometimes writing down what's happening every time in between each term can help us determine what the pattern is. Number 3 is -1, 3, -9, 27, -81. So I'm multiplying by -3 here, right? So -1 times -3 is 3. And then 3 times -3 is -9, and so on. So -81 times -3 is positive 243. If I multiply that by -3, I get -720. And multiply that by -3, and I get 21, positive 2187. Dot, dot, dot. Okay? And then number 4, it's kind of hard to see, like, it's not adding the same number every time. It's not multiplying by the same number every time. So I'm going to write down what's happening here, right? So I add 2. Then I add 3. Then I add 5. Then I add 7. then I add 11. So I notice 2, 3, 5, 7, 11 are all prime numbers, right? It's not all odd numbers, but they are prime numbers. So my next prime number after 11 is 13. So 29 plus 13 is 42. My next prime number after 13 is 17. So 42 plus 17 is 59. And then my next prime number after 17 is 19. So 59 plus 19 is 78. So here I'm just adding prime numbers. Okay, so all four of these are examples of a sequence. So a sequence is just an ordered list of numbers. Here's the definition right now. Okay, a finite sequence is one whose domain consists of any number from 1 to an ending value, okay? So, meaning like 3, 5, 7, 9, without that dot, 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 this is a finite sequence, right? This is, n is my term number. So this is the first term, second term, third term, fourth term, right? So there's 4 terms in this sequence. An infinite sequence is where n goes on forever. So if this becomes dot, 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 now it goes on to infinity, right? There's infinitely many terms. So a finite sequence is one where the number of terms is set and you can count them. Whether or not you want to count them, right, is something different. But a finite sequence basically has an ending, whereas an infinite sequence, the number of terms goes on for forever. So hopefully that makes sense. So the numbers, right, are called terms. So that your outputs are called terms. And this is the notation that we use. So if I have that sequence again, right, like the first term, we would notate it with a sub 1. So my first term is 3. And then a sub 2 would be my second term, and that is 5. And then a sub 3 would be my third term, right? That's 7. A sub 4 is the fourth term, which is 9. And then a sub n would be the nth term, and that's usually your equation. So in this case, a sub n would equal 2n minus 1. Because I'm adding 2 every time, right? And my 0th term is 1. So a sub n, this would allow me to find the 50th term. If this goes on forever, I could find a sub, oh my gosh, so sorry, my dog is moving around on me. I could find a sub 50 by plugging in 50. So the 50th term would be 99, right? So this a sub n allows us to find any term in the sequence that we would like. So hopefully some of this looks familiar from previous classes. Okay, so here's an example, a different example. So a sub n equals 5n minus 5 represents this sequence. If I plug in 1, 5 times 1 is 5, minus 6 is negative 1. So this is a sub 1. If I plug in 2, I get 10 minus 6, which is 4, right? And so on and so forth. This is called the explicit equation. And this means that I can plug in any number I want. If I want to know, like I said, the 50th term, I plug in 50 and I solve. Okay, so it allows us to find any term in the sequence. Here's something different that maybe we haven't seen before. If I have a factor of negative 1 to the n, this is going to cause my sequence to alternate between positive and negative values. Positive and negative. Right, so negative 1 to the 1 is negative 1, but negative 1 squared is positive 1. And then negative 1 to the third is negative 1, and then negative 1 to the fourth is positive 1. So it alternates between positives and negatives. Okay, so let's look at an example to kind of help us review here. It says, write the first 4 terms of the sequence whose nth term or general term is given. So I just want the first 4 terms. So first term would be a sub 1, which just means I plug in 1, right? So a sub 1 here is 3 minus 2, which is 1. My second term would be 3 times 2 minus 2, which is 4. My third term would be 3 times 3 minus 2, which is 7. And I don't know why I wrote 5. And my fourth term is going to be 3 times 4 minus 2, which is 10. And that's it. All right, I'm just plugging in the numbers and solving. Same thing for B. My first term is 3 plus negative 1 to the 1. Well, negative 1 to the 1 is negative 1, so 3 plus negative 1 is 2. My second term is going to be 3 plus negative 1 squared. Negative 1 squared is positive 1, so 3 plus 1 is 4. Then my third term is going to be 3 plus negative 1 to the third. Well, negative 1 to the third is negative 1, so 3 plus negative 1 is 2 again. And then a sub 4, is 3 plus negative 1 to the fourth. And negative 1 to the fourth is positive 1, so 3 plus 1 is back to 4. And that's it. So it just wants me to write the first 4 terms, so I just plug in 1, 2, 3, and 4. Example 2 wants me to write the first 5 terms of this sequence. Okay, so we're going to start with the first term. So a sub 1 is equal to negative 1 to the 1 over 2 times 1 minus 1. So negative 1 to the 1 is negative 1. 2 times 1 is 2, minus 1 is 1. So a sub 1 is negative 1. Maybe we make a little list over here. A sub 1 is negative 1. Okay, a sub 2 gets me negative 1 squared over 2 times 2 minus 1. Negative 1 squared is positive 1. 2 times 2 is 4, minus 1 is 3, so I get 1/3. So my second term is 1/3. For my third term, a sub 3, I have negative 1 to the 3 over 2 times 3 minus 1. Negative 1 to the third is negative 1. 2 times 3 is 6, minus 1 is 5, and I get negative 1/5. So a sub 3 is negative 1/5. Fourth term, we're going to plug in 4. So I have 2 times 4 minus 1. Negative 1 to the fourth is 1. 2 times 4 is 8, minus 1 is 7. So my fourth term is 1/7. And then it wants the first 5, so I have to do the fifth term of negative 1 to the fifth over 2 times 5 minus 1. Negative 1 to the fifth is negative 1. 2 times 5 is 10, minus 1 is 9. So a sub 5 is negative 1/9. So just being able to plug in values, right, and solve for the first 5 terms or the first 3 terms, 4 terms, whatever it's asking you to do. Now let's look at going the other way. What if I'm given the first couple terms? How can I write the explicit equation, right? Or how can I write the expression of the nth term? So here, I usually like to see if I can find a pattern, right? So this is my first term, this is my second term, this is my third term, this is my fourth term. So there's lots of ways to look at it. The first way is you can say, okay, am I adding or subtracting the same number every time? And if I am, here I'm adding 2, adding 2, adding 2. So that tells me that my slope is going to be 2. Okay? And then I want it so that when I plug in 1, I get 1, right? When my n is 1, I get 1. So if I plug in 1, 2 times n is 1, that's 2. So then I have to subtract a 1 to get 1. And then we check it to see if it works, right? 2 times 2, which is n, right? My n is 2. 2 times 2 is 4, minus 1 is 3. So that's good. 2 times 3 is 6, minus 1 is 5. 2 times 4 is 8, minus 1 is 7. So this is good. So our expression is that, double n and subtract 1, right? So we double n and we subtract 1. Okay, here looks maybe a little bit more difficult. So let's do it on the bottom so we can see it better, right? N is 1, 2, 3, 4. So this one seems a little bit harder. I'm not adding the same number every time. I am not multiplying by the same number every time. So I have to come up with some other pattern. Another common one is looking at squares or square roots. Okay, so if I square 1, so let's just try this. If I square 1, and this might not be it, right? Sometimes you start writing and it doesn't work. So 1 squared is 1. To get to 2, I would have to add 1. So that works for this first term, right? That works for the first term. If I plug in 1, I get out 2. Now let's see if it works for this one. If I plug in 2, 2 squared is 4, plus 1 is 5. If I plug in 3, 3 squared is 9, plus 1 is 10. 4 squared is 16, plus 1 is 17. So this works. Okay, so terms are 1 more than n squared. Okay, and now this part says find a sub 16 in part B. So I want to know the 16th term. Well, I have the equation, so a sub 16 is going to be equal to 16 squared plus 1, which is 256 plus 1. So the 16th term in that sequence is 200 and that's a backwards 557. So having the explicit equation here is really helpful because then I can find any term that I want. Okay, so when we have the explicit equations, all I have to do is plug in the number that I want, right? If I want to know the 20th term, I just plug in 20. If I want to know the 100th term, I plug in 100. Okay, so that's why the explicit equation is so helpful. The other type of equation that we look at is a recursive equation. So what makes the recursive equation different is that you can have all sorts of different types of sequences that maybe you can't write an explicit equation for. But what you need to know in order to write a recursive equation or in order to write the terms of a recursive equation is you need to know the terms prior. So in order to know the 10th term, I would have to know the 9th and the 8th and the 7th and the 6th, right? And so on and so forth. So that makes it kind of difficult, right? If I asked you to find the 30th term, you're not going to find it recursively because you would have to find all the terms in front of it in order to know the 30th, which is a pain. Okay, so recursive sequences, usually they give you at least the first term, and then they give you some sort of pattern to follow. So let's look at here. It gives me that the 0th term is 1. So let's write it here. Why not? Then it gives me the first term is 1. Okay. Then it says the next term, so like if this is 2, right? So like a sub 2, it's equal to a sub 2, k is 2, so 2 minus 2 is 0, so this would be equal to a sub 0 plus, and then k minus 1 is 1, so a sub 1. So a sub 2 is equal to 1 plus 1, because a sub 0 is 1, a sub 1 is 1, so 2. So my next number is 2, right? And then the third sequence, or the third term, excuse me, k is 3, then this would be a sub 1, because 3 minus 2 is 1, so this would be a sub 1 plus k minus 1, 3 minus 1 is 2, a sub 2. Well, my first term was 1, and my second term was 2. So I get 3. Right? And then I can keep going. To find the fourth term, it would be 4 minus 2, so a sub 2, plus 4 minus 1, which is a sub 3, which is equal to the second term was 2. The third term was 3, so I get 5. So the next number is 5. Fifth term is equal to 5 minus 2 is 3, so a sub 3, plus 5 minus 1 is 4, so a sub 4. The third term was 3, plus the fourth term was 5, so I get 8. So if you just notice, it's the two previous numbers added together. So I can keep going here, but I'm not going to. Hopefully this sequence looks familiar. This is a super famous sequence. It's the Fibonacci. I'm going to try to spell it correctly. Right? It's the Fibonacci sequence. We see this all the time in nature, in the way seashells coil, in pine cones and sunflowers. It's used in astronomy. So many different real life applications of this sequence. The golden ratio, so many things. So, but this sequence, there's no way to write it explicitly. If I want to know the 20th number in this sequence, I would have to know the 19th and the 18th. But in order to know the 19th and the 18th, I'd have to know the 15th, 16th, 17th, right? And in order to know those, I'll have to know the ones before them. So I can't just plug in 20 into this equation, because I would have to know all the numbers in front of it as well. So that's how a recursive sequence works. You're given the first number, the first two numbers, something like that, and then you're given a pattern to follow. So looking at like our example here, I'm given that it wants the first 4 terms, first of all, right? So just gonna write it off to the side, right? So I'm given that the first one is 3. Awesome, right? But I also want the second term, and the third term, and the fourth term. So we're going to figure that out. So here, a sub n, I want the second term. So n is 2. So this is going to be equal to 2 times a sub 2 minus 1. So that's going to be a sub 1. Well, a sub 1 was 3. So 2 times 3, which is 6. Notice that this equation only works for n's greater than or equal to 2. I could not plug 1 into this equation, nor would it help me because I already know 1. But just so that we're aware, right, I can only plug in numbers 2 and higher. Oh, I didn't see the plus 5. That's why you guys have to yell at me. Thank you. Right, I didn't see the plus 5, so plus 5. So this is 2 times 3 plus 5, which is 11. So a sub 2 is 11, not 6. Okay, to find the third term, it would be 2 times 3 minus 1 is 2, so this will be a sub 2 plus 5. So it'll be 2 times that 11 plus 5. So 22, I don't know why I wrote 55. 22 plus 5 is 27. So basically all this is saying is, hey, you take your current number in the sequence, you multiply it by 2, and you add 5. And that'll get you your next term, right? So my fourth term is I take 2 times the one I just found, a sub 3, and I add 5, right? So 2 times, my dogs are about to bark, just excuse me. It's okay, don't bark. No, never mind. So it'll be 2 times a sub 3, well, a sub 3 is 27, plus 5. Right? So 2 times 27 is 54, plus 5 is 59. If I wanted to find the next one, I would just multiply 59 times 2 and add 5. So it's just a pattern, right? Over and over and over. Take your number, multiply it by 2, add 5. Take the next number, multiply it by 2, add 5, and so on and so forth. For B, same thing. I want the first 4 terms. So I'm going to make a little list here. And I know that my first term is 2, so that's exciting. And now I want to find the second term. So a sub 2, n is 2, is equal to n, well, n was 2, times a sub 2 minus 1, so a sub 1. Okay, so that would be 2 times a sub 1 is 2, and that gets me 4. So my next number is 4. The next term, now n is 3, so it'll be 3 times a sub 2. So it'll be 3 times my previous number, which was 4, and I get 12. And then my last term, now n is 4, so it'll be 4 times n minus 1 is 3, so a sub 3. Right, so 4 times 12, which is 48. If I wanted to find n sub 5, I would do 5 times 48. So on, and then so on and so forth. It continues on. And then the last one, C, I want the first 4 terms. So a sub 1, a sub 2, 3, and 4. I'm given that the first term is 1/3, and I'm given that the second term is 3. So I'm actually given 2 terms. That's exciting. So now I just need to find the third term. So n is 3. So a sub 3 minus 1, so that's a sub 1. Sorry, 3 minus 2 is 1, times a sub 3 minus 1 is 2. So the first term times the second term. Well, my first term is 1/3, times my second term is 3. If I want to make it a fraction, I can, 3 over 1, right? And I get 1. 3 over 3, which is 1. So my third term is 1. Then to find the fourth term, now n is 4, so 4 minus 2 is 2, so that's going to be the second term, times 4 minus 1 is 3, so times the third term. Well, my second term is 3, times my third term is 1, so I just get 3. And there's my first 3 terms. Sorry, my first 4 terms. There's 4 there. Okay, so hopefully that looks familiar. We feel okay. If you have any questions, make sure we reach out. We're going to look at our second objective now, which is looking at factorials, which may be new for us. All a factorial is, first of all, the notation is an exclamation mark. Okay, and so what that is whatever n is, I take that number and all the numbers before it all the way down to 1, and I just multiply them together, right? So, if I have 4 factorial, that's the same thing as 4 times 3 times 2 times 1. 6 factorial would be 6 times 5 times, oops, I did it as a point, not times, times 4 times 3 times 2 times 1, right? And so on and so forth. 20th factorial will be 20, 19, 18, 17, you know? So it can get very big very quickly. So there is a way to do this on your graphing calculator. If you go under math, and I'll show you on the calculator here in a second, but if you go to the math button, and then you go to the right where it says probability, it's PRB. So scroll to the right to get to probability, and it's option number 4, which is the factorial. Okay? And that will allow you to enter factorial into your calculator. So let me show you what that looks like on the calculator real quick. Okay, so here's our calculator. So the factorial button, if I want like 20 factorial, I'm going to go to math, which is right under alpha. And then over here, sorry, it's PROB, not PRB. Fix that in your notes. And then number 4 here is factorial. So I hit 4. And it just brings that exclamation mark in, and I hit enter. Now this is a massive number, right? It's 2.4 times 10 to the 18th. So it's 2.4, and then move that decimal place 18 times. Okay, so it's a huge number. Something a little bit more manageable would be like 4 factorial. 4 times 3 times 2 is 24, right? 4 times 3 is 12, times 2 is 24, times 1 is 24. Or 8 factorial, right? So you can see how these numbers get big very quickly, right? 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 40,320. So you don't have to actually in your calculator go 8 times 7 times 6. Ugh, don't do that. Okay, use your factorial button. So let's look now at sequences that involve factorials. So here, example 5 says, write the first 5 terms of the sequence given by a sub n equals 2 to the n over n factorial. Begin with n to the 0. And I did miss that part here. And 0 factorial is always 1 by definition, okay? So it's always 1. So if I plug in 0 first, a sub 0, I have 2 to the 0 over 0 factorial. 2 to the 0, any number to the 0 is 1. 0 factorial by definition is 1, so I get 1. So a sub 0 is equal to 1. A sub 1 is equal to 2 to the 1 over 1 factorial. 2 to the 1 is just 2. 1 factorial is just 1 times 1, right? So it's just 1. So I get 2. So my first term there is 2. A sub 2 is going to give me 2 to the second over 2 factorial. Well, 2 squared is 4. 2 factorial is 2 times 1, which is 2. So I get 2. So my second term is also 2. It's okay, right? It's just following the pattern. Third term, 2 to the third over 3 factorial. 2 to the third is 8. 3 times 2 is 6 times 1 is 6. So I get 4 over 3. Always reduce your fractions. So a sub 3 is 4 over 3. A sub 4, if we keep going, 2 to the 4th over 4 factorial. 2 to the 4th is 16. Over 4 factorial is 24. 4 goes into both of those. 8 goes into both of those, and I get 2 thirds. So my fourth term is 2 thirds. And then my fifth term, we 2 to the 5th over 5 factorial. 2 to the 5th is 32 over 5 factorial is 120. Now, when you get to something like this and you don't know, like, it takes forever to reduce it, you can always reduce it on your calculator. 32 divided by 120 gives you a crazy decimal. Then if you go into math, your first option is fraction. Hit enter. You're saying, hey, I want to take this decimal answer and I want to turn it into a fraction. And it will reduce it for you. Okay, so this is 4 cool, words, right? 4 over 15. And so it reduces it for you. So then your fifth term is 4 over 15. So hopefully that makes sense how you can do that on your calculator here. Okay, we have our first U try. I want you to go ahead and pause the video and find the first 5 terms of this sequence, 20 over n plus 1 factorial. Okay, so here's the answers for this problem. Hopefully give it a shot. I just realized this is a really ugly 6. You can't read it. So double check your work here and make sure everything looks good. I just plugged in. I started with a sub 1, my first term, and I ended at the 5th term because I want the first 5 terms. And so I just plugged in 1, right, 2, 3, 4, 5. And then used my factorial button on my calculator to figure out what those numbers were, and then used my calculator to reduce it. Okay. So hopefully we're feeling good there. We're going to look at some simplifying of factorial expressions, right? Like what if I have 8 factorial over 2 factorial and 6 factorial? We're going to use A and B to kind of help us come up with a pattern for what we're going to be looking at later on in the unit. So 8 factorial, right? If I think about this, I don't want to have to plug this into my calculator. And even, if it's a non-calculator portion or whatever, the easiest thing to do here is to just write it out without actually multiplying it, right? So there's that. And this is over 2 times 1, right, times 6 times 5 times 4 times 3, 2 times 1. So since these are all multiplying, I can just cancel. So 6 can cancel with 6, 5, 5, right? I can just do this, okay? And then I can cancel here. 2 goes into 8 4 times. So then that gives me 4 times 7 on top, which is 28, and 1 on the bottom, so it's just 28. So a nice little simple way to reduce that. Just write it out. And typically I don't write the ones because they don't really do anything when you're multiplying. So like for B, I would do 2, and then times 6, 5, 4, 3, and 2. And then on the bottom, I have a 3 and a 2, and then a 5, 4, 3, and 2. So here I would cross off my 5, 4, 3, and 2. My 2's can cancel. And then I'm just left with 6 over 3, which is just 2. And that's it. So a lot easier way to simplify it, right? For C, if I write this out as a general pattern, I would have n, and then I would have one number smaller than n, so that would be n minus 1. And then I would have 2 numbers smaller than n, and 3 numbers smaller than n, and right all the way down to 1, right? Depending on what n is. That would be the top. And then on the bottom, I would have n minus 1, because that's the first number. And then I would have one number smaller than that, so it would be n minus 2, and then one number smaller than that, so n minus 3, all the way down to 1. So things that would cancel, right, the n minus 1s, the n minus 2s, the n minus 3s, all the way down to 1. So the only thing, the only thing that I'd be left with is this n. So this is just equal to n. And then it says, to check A and B using your calculator, and you're more than welcome to do that. But we got it right. So that's using factorials. Hopefully we feel good. If you have any questions, make sure you reach out. Our next objective is to look at summation notation for sums. Okay, so far we've only looked at sequences, right? That pattern of numbers. A series is the sum of the terms of a sequence. So again, if I have that same old sequence that we had before, right? 3, 5, 7, 9, and it ends, the summation would be the sum of this if I added them together. 9 plus 7 is 16, 21, 24, right? So the summation, and we use this Greek letter sigma, the capital letter, sigma, for summation. And this says, hey, starting at term 1 and ending at term 4, what is the sum of this? Right? And so then I could add up blah, 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 and I get 24. So a series is when you're adding the terms together, okay? And it can be finite, like the one I just showed you, or it can be infinite and go on forever, which is kind of weird, right? We think, oh, you can't add numbers that go to infinity, but you can. Okay, so we're going to look at how we do this. There's a couple properties we want to look at first. So here, right, the I equals 1 just tells me I'm starting when A is 1. And then n means I'm going all the way to n. So if n is 7, I would add up term 1, 2, 3, 4, 5, 6, and 7, right? If n is 20, I would add the first 20 terms. If I is 5 and n is 10, I would add terms 5, 6, 7, 8, 9, and 10. So this just tells you what term to start with, what term to end with, add them together. Okay? And so that's called the index. And so it's like the lower limit and the upper limit. And then if we're going to infinity, n up here, the upper limit would be infinity. So some properties here. If I just have a constant, like a number, right? If it's the summation of 3, right, from 1 to 4 or something. I'm just making stuff up, right? This is really 3, which is the first term, plus the second term, which is 3, plus the third term, which is 3, plus the fourth term, which is 3. So instead of having to do that a million times, I can just multiply 3 times whatever that upper limit is for. So that's what this first one is saying. Okay. The second one is saying, hey, if I have a pattern and it's being multiplied by a constant, I can find the sum first and then multiply the constant later. So that's actually really helpful if I have a ton of numbers, right? And it's just adding them all up and I'm like, oh my gosh, I can't even. So, and the numbers, it makes the numbers quite big when you have this constant being multiplied. So if you can multiply the constant by the end, it's very helpful. And then the last one, if I'm adding, two terms together within the summation, I can add them separately, or I can find the sum separately and then add or subtract them together, which sometimes is helpful to be able to break them apart. Okay, so let's look at some examples of these, and we'll have a good old time. Okay, so the first one here, this is saying I want starting with I at 1 and going to I is 5, what's the sum? Okay, so there's a couple ways that we can do this. The first way is that we can take my first term, which is 3 times 1, and I'm going to add it to my second term, which is 3 times 2. And then my third term is 3 times 3. And then my fourth term, is 3 times 4. And then my fifth term is 3 times 5, right? And I can add them all up and I get 45. That's great. But using that property up above, I also can just do 3. I take this 3 out, and then I just do the I. Well, the I would be 1 plus 2 plus 3 plus 4 plus 5. And if I add these together, 3 and 3 is 6, 10, 15, 3 times 15 is 45. And so for this one, it's fairly easy to do it either way. But when we get into bigger numbers, or what if you're doing more than 5 terms or whatever, sometimes it's easier to pull this 3 out, right? To pull the 3 out and find the summation of just I, right? Plug in I plus 2 plus 3 and so on and so forth. For B, again, notice I'm starting with the third term. So I'm starting with 1 plus, we don't really need parentheses there. 1 plus 3 squared, right? Plus 1 plus, 4 squared plus 1 plus 5 squared plus 1 plus 6 squared. Oops, I forgot the one. I said it, but I didn't write it. 1 plus 6 squared. Right, and I'm more than welcome to do that. This gets me 10 plus 17 plus 26 plus 37, which equals 90. Or, and again, maybe for this one it's not as helpful, right? I can break this up. I can do the sum from 3 to 6 of 1 plus the sum from 3 to 6 of k squared, right? And so if I add this together, that gets me at 3, that's 1, plus 4 is 1, plus 5 is 1, plus 6 is 1, plus, and then 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36. And then I still get 90. So either way, whatever kind of makes sense to you. Sometimes, like this one's not so bad, right? This is fine to just plug it in like this, but sometimes when we get into harder ones, it's nice to use those properties. Okay, the last one, 8. Notice it wants me to start at 0. So I have 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3, right? And I am going all the way to 8, which of course I won't be able to fit. Plus 1 over 7 factorial plus 1 over 8 factorial. Now, this is definitely something that I would like to do in my calculator, right? I don't want to have to figure out what all these are and all that kind of stuff. So there is a way that we can enter this summation, into our calculator. So I'm going to show you how to do that right now. So let's pull up our calculator here. So we're going to go under Math, and we're going to go up. It's actually faster if you go up to 0 where it says summation, or you can just hit 0 if you remember that it's 0. Okay. And it allows us to do this. Now here, the alpha wants what letter are we using? In this case, we're using N. So we need to find N in our alphabet. And here it is, it's above the log button. And we're starting at when N is 0. And then we hit up, and we're going to when N is 8. And then it wants me to enter the function, right? So 1 divided by, I have to go alpha N And then I need that factorial. So I'm going to go math over to probability number 4. So it's important to know where this stuff is on your calculator because this could take a long time for you to enter in your calculator if you don't know where the summation button is or if you don't know where the factorial button is. Okay, but I'm going to hit enter and I get 2.71827 blah blah blah. I'm going to round it. So I get 2.7, let's just do 718 dot dot dot. And that is a way to do that on your calculator. Now, there will be times when, like for these, for example, D and E, I wouldn't want you to use your calculator on it. I'd want you to show me. Actually, for all of these, the only time I'm really like, okay, let's use our calculator is when we get into some really, really difficult ones, okay? So I want you to try D through F. You're going to do this without your calculator. You're more than welcome to check your answers on your calculator. But go ahead and hit pause, try these 3, and then hit play, and we'll go over it. Okay, so let's check our work for these first 2. I tried to do them like, I did the first one, D, using the property that I can take this 2 out, right? So I did 2 and then the summation of I squared. So here's the 2, and then I did 1 squared, 2 squared, all the way up to 6 squared. Found the sum of that, which was 91, and then just multiplied by 2. If you did it the other way, right, where you did 2 times 1 squared plus 2 times 2 squared, and so on, you should have still gotten 182. So either way, you get to the answer, okay? For E, I just went ahead and plugged in 3, 4, and 5 for K, and I got 47. Again, you could have done 2 to the 3rd plus 2 to the 4th plus 2 to the 5th, right? That first part. And then minus, if I plug in 3 here, it's 3. Plus, if I plug in 3 for 4, it's 3. Plus, if I plug in 3 for 5, it's 3. And either way, you would have gotten 47. Okay? For the last one, if I plug in 1, there's nowhere to plug in 1, so it's just 4. If I plug in 2, I get 4. If I plug in 3, I get 4. If I plug in 4, I get 4. If I plug in 5, I get 4. So remember that property that you can just take these 2 numbers and multiply them together, right? So you can just do 4 times 5. And either way, you will get the same answer, which is 20. And that's it. Hopefully we feel good there. Okay, now let's look at going the opposite direction, right? What if I'm given the terms, right? If I'm given all the terms that are being added together, what does the summation look like? So now I'm trying to write the summation. So I can draw my sigma. And I need to figure out what is the equation, where am I starting, where am I ending, right? So I have to find the index, the upper limit, and the sequence. So if I look here, the one thing I notice that's staying the same is it's always being squared. So since that's not changing, I know that that's going to be in my equation, right? That's going to be part of my summation. And then I have 1, 2, 3. It's just going up by 1 every time. So I'm confident that I can just say that it's I or N or K or whatever variable you want, I squared. And that means that my starting value, the first number that I plug in for I, is 1. The last number I plug in for I is 9. And there's my equation. Or there's my summation notation, excuse me. Okay. For B, it's a little bit harder, but this is my biggest clue right here, right? It's telling me what I'm doing. So I'm going to draw my sigma. Okay, this is telling me what it's doing. It's 1 over 2. I can't use n because that's going to be my upper limit. So I'm going to use I minus 1. This is what's happening every time. Okay, and I know that my upper limit is going to be n. N is the last number I plug in, and that's how I get this, right? If I plug n in for I get this. And I need to figure out where I start, right? What do I plug in to give me 1? So if I plug in 0, let's try that. 2 to the 0 is 1. Oh, sorry. If I plug in 0, 0 minus 1 is -1. And 2 to the -1 comes up, becomes 1/2. And so that's not going to be good, okay? If I plug in 1, I tried 0, let's try 1. If I plug in 1, 1 minus 1 is 0, 2 to the 0 is 1, and 1 over 1 is 1. So that tells me that my I is starting at 1. Because if I plug in 1 for I get my first term, which is 1. Okay, here, I have to look. 6 to 8 is adding 2, adding 2, adding 2. So I'm adding 2 every time. But if let's try it. And let's look. So if I add 2, if I do like I plus 2, right? In order to get 6, I would have to start at 4, right? But then when I plug in 5, 5 plus 2 is 7, not 8. So that's not right. So that's not the correct equation, right? And so sometimes we just have to try something and then try it again. Okay, these are all even numbers. So maybe instead of I plus 2, it's 2 times I. And in order to get 6, I would have to be 3. So I would start at 3. And if I is 4, it'd be 8. If I is 5, it's 10. So that works, okay? And then I need to figure out what's my upper limit. Well, 2 times what is 32, right? My upper limit is 16. So I'm just kind of using pieces that I'm given to plug things in and see what works. And if it doesn't work, I try something else, okay? Okay, let's look at D. I'm going to go ahead and draw my summation. Okay. So something that I noticed that's the same in every single one of these is that there's an A. So that's good. And there's an R, except for right here, right? So that's fine. And so I need to know what I start at, right? I equals, so here there's no R. So since there's no R, that means the R went away. So the exponent on the R, let's call that I, excuse me. So the exponent on the R would have to be 0. So I would have to start at 0, right? R to the 0 is 1, so that just goes away, and I'm left with A. And then I would go all the way up to 14, right? So if I plug 14 in for I get the last term. Now, that's not the only way to do it. A lot of these have other ways, right? If I could do a R to the I minus 1. And if I did that, I would start at 1 and it would go to 15, right? Or I could do I minus 2 and then it would start at 2 and go to 16. And so sometimes there are multiple ways to do this, but usually just by plugging things in, you'll get something like this. And then the last one, summation. I see that it's A plus D to the something, so I'm going to go ahead and A plus D, and the thing that's changing is my exponent, so that's going to be my I. And then I have to figure out where do I start. So I is equal to, well, the exponent here is a 1. So I is 1, is the first, is the lower limit. And then it goes all the way up to N. So that's going to be my last one, right? If I plug N in for I, then I get this last term. So it doesn't always have to be a number up here. Keep that in mind. Right, in this case, my upper limit is N. So I could plug in 12 for N, or I could plug 17, or I could plug in 45, or whatever for N. And it would give me the summation. Okay, so let's look at actually what we call partial sums of sequences and finding the sum there. And then we're going to go in and look, what we're looking at now is infinite series. How do you add something if it continues on for forever? So here we have the sum of the first n terms of a sequence is called a finite series, or the partial sum of a sequence. So here, this series goes on to infinity, right? That I replace I all the way up to the infinity. So it wants me to find the third partial sum, meaning the first three terms. So this is, you add the first three terms. So that's what that means, the third partial sum. So partial sum, because the actual series goes on forever, but I just want that little chunk. Okay, so let's do that first. So that's going to be the summation. I is going to start at 1, and it's going to go to 3 of this series. Hard to write small. So I'm just going to add, right? That gives me 3 over 10 to the 1 plus 3 over 10 squared plus 3 over 10 cubed. And if I add these up, I get 0.3 plus 0.03 plus 0.003. So if I add it up, I get 0.333. And that does not continue on forever. It's just 0.333 because it's only the first three sums. Okay? Then it wants me to find the sum of the whole thing. Well, how do you find the sum of something that adds on forever, right? So if I want to do that, this is going to take a long time. No, I'm just kidding. We're not going to actually go on for forever. Oops, it's not 10 times I. 10 to the I, right? So this gets me, I know that the first term is 0.3, second term is 0.03, third term is 0.003, and as you can guess, it's going to just continue on adding zeros, right? Dot, dot, dot. So if I add this up, it goes on for forever. It keeps adding threes for forever. So I add this up and I get 3, 3, 3, 3, 3, 3, right? Blah, 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 blah. And it keeps going. And at this point, we know that 0.33333 to infinity is just 1/3. So we actually can add up something that goes on to infinity. Right? We're not physically adding every single number together, but we know that this 0.33333 is equal to 1/3. And so that's, how we're able to add something that does go on to infinity. And I do want to tell you there is a little trick with this. So 0.333, anytime you have the same number repeating over and over again, what that's really equal to is whatever that number is over 9, like automatically. It's always over 9. And so then 3 over 9 just reduces to 1/3. So I want you to keep that in mind when you are trying the next one, right? Because it's 5 over 10, so it's a little bit different. Oops, I didn't clear it. So I want you to try this one. Just use, the previous problem. Pause the video, give this one a try, and then let's see how you did. Okay, so hopefully we gave this a shot, right? I want the third partial sum. So n is going from 1 to 3. 5 over 10 to the n. It doesn't matter if it's n or I or whatever, right? It's all going to be the same thing. So this is going to be 5 over 10 to the 1 plus 5 over 10 squared plus 5 over 10 cubed, because I want the third partial sum. And if I wanted the fifth partial sum, I'd have to add 5 of them together. So this is 0.5 plus 0.05 plus 0.005. So the third partial sum is just going to be 0.555. Now, if I want to find the sum of the entire thing that goes on to infinity, it's going to be the same idea. So n equals 1, 5 over 10 to the n, right? So I know the first term is 0.5, second term is 0.05, and yes, this goes on forever, right? I think you get it. So this ends up being 0.5555 repeating, going on forever. Well, anytime I have that same number repeating over and over and over, it's just that number over 9. And then reduce it if you can, but in this case you cannot. So that's like when you have like 0.666666, right, going on forever. That's 6 over 9, which reduces to 2/3. Okay, like 0.77777 is 7 over 9, which doesn't reduce. Okay. And so that's kind of cool, like that crazy argument that like 0.9999 repeating is equal to 1, and people will argue against it or not, but 0.999 repeating is equal to 9 over 9, which is 1. So it is kind of crazy to think about that 0.999 repeating all the way to infinity is actually 1. But that's wise because it's that number 9 repeating over 9, which is 1. Just a little fun fact thrown in there for you. Okay, last problem here is an application problem. It says from 1970 to 2004, the resident population of the United States can be approximated by the model a sub n equals 205.5, blah, 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 this whole thing, where n is 0 to 34, because that is the range of years, right? 0 is 1970, 34 is 2004. And it says find the last terms of the finite sequence, the last 5 terms. So here I don't even have to add them up. I'm just finding the last 5 terms. So I like that. I'm going to scroll down just a little bit there. So I want to find the last 5 terms. So that's going to be, I don't know why I put parentheses. Sorry. A sub 30, right? 31, 32, 33, 34. So then I'm just going to plug these in. 205.5 plus 1.82 times n, well, n is 30, plus 0.024 times n, which is 30 squared. I'm going to show you a lovely little trick on your calculator. So I'm going to plug it in. 205.5 plus 1.82 times 30 plus 0.024 times 30 squared. And I hit it. So there it is. 281.7. Remember, that's in millions, right? So this is 281.7 million people is in year 2000. Okay. So when we go to do the next one, right, it's the same thing. Oh, we have to plug in 205.5 plus 1.82 times 31 plus 0.024 times 31 squared. We'll have to paint it into that whole thing into your calculator again. So if you go second enter, it'll take what you just entered and just rewrite it for you. And then you can just go through quickly and change all those 30s to 31s and hit enter. There it is, 284.984, right? So 284.984 million people in the year 2001. Go ahead and find the next 3. right? Because we want the last 5 terms. So go ahead and find a sub 32, a sub 33, and a sub 34. And when you're ready, check your work, hit play, and we'll have the answers here for you. Okay, so go ahead, check your work here. In 2002, there was 288.316 million people. 2003 was 291.696 million people. And then in 2004, 295.124 million people. So that's just practice entering it into your calculator. Hopefully that's nothing too crazy there. I know this was a really long lesson. I promise the other ones won't be as bad. If you have any questions at all, make sure you reach out, and we'll talk to you guys soon.